Before grade 12, it's really important that I at least introduce you to the idea of a trigonometric identity. So an identity is very similar to an equation, but it's an equation that is always true regardless of the value of the variable. So what I mean by that is if you have an equation that says x squared equals 9, we know that x is equal to, we'll take the square root of both sides, plus or minus 3. So this is an equation because there's only two values that hold true. An identity is different because no matter what we plug in for our values, it should always be true. Obviously, there are a few exceptions, like we can't divide by 0, but for the most part, it's always going to be true. So there are some identities that you're just going to need to know before you get to grade 12. We've talked about a few of these. So we've talked about all of our reciprocal identities. So these three identities at the bottom. Cosecant theta is 1 over sine, secant theta is 1 over cos, and cotan is 1 over tan. There are two more that I'm going to be telling you about today, and those are going to be used as we work through these examples. So again, this is not a full lesson. I'm not giving you an assignment, but I do think that at least listening to this video and trying to follow along as I work is going to be important and when we get to grade 12. Obviously, we're going to have to redo all of this before we can move on, but I think seeing it will just make it a little bit easier for you. So the first new identity that we're going to be talking about is the Pythagorean identity. So sine squared theta plus cos squared theta is equal to 1. So obviously this is similar to the a squared plus b squared equals c squared. And if you think about the unit circle, that probably makes even more sense. So we know that our unit circle has a radius of 1, so that's where this comes into play. And we know that the x value and the y value can be related to cos of theta and sine of theta. So when you think about it, the Pythagorean identity really does make a lot of sense. The next identity that you're going to need to remember and is new right now is the quotient identity. And it's just really a way to relate tan to sine and cos. Now, if you think about tan, we know that tan is opposite over adjacent. And so when I look at this little triangle that I have drawn here in my unit circle, if I have my theta in here, my opposite is my sine, and my adjacent is my cos. So again, this identity probably makes a lot of sense. Now, from my Pythagorean identity, I can derive a few more identities. So there's no need to memorize these because it's just the rearranged version of this. So if I wanted an identity for sine squared theta, it would be 1 minus cos squared theta. So I just took this and moved it over to the right-hand side. And same thing if I wanted an identity for cos squared theta. It would be 1 minus sine squared theta. All of these are going to be useful as we attempt our examples. In this first example, it says that we are going to be using basic identities to prove an identity from one side. So our first proof is going to be proving that tan squared theta plus 1 is equal to secant squared theta. So I'm going to be giving you a few hints as we go through. So the first hint is that you always want to switch your tan theta to sine over cos. And you always want to switch your reciprocal. Oh, it's getting a little messy here. You always want to switch your reciprocal. All right. So, going forward, I'm going to be working with the left-hand side. So I'm going to be attempting to turn tan squared theta plus 1 into secant squared theta. So left side, tan squared theta plus 1. So the first thing that I'm going to do is switch my tan squared. So I'm going to switch it to sine squared theta over cos squared theta. Now that should make sense to you. If tan is equal to sine over cos, it only makes sense that tan squared would be sine squared over cos squared. And if that doesn't make sense to you, you could always write it as sine theta over cos theta squared, and then you know that the 2 would have to go into both. So maybe that will help you a little bit more. At this point in time, when I look at this, I am going to try and get a common denominator. So I know that anytime I'm adding, I need a common denominator. So I'm going to have sine squared theta over cos squared theta, and I'm going to turn this 1 into cos squared theta over cos squared theta. So really, I haven't changed anything. This is still just 1, but I have a common denominator, so now I'm able to add. So what I have on the top is sine squared theta plus cos squared theta, and all of that is over cos squared theta. Now when I look at this, and maybe you're thinking this too, I see that my numerator is sine squared theta plus cos squared theta. I know that this is the Pythagorean identity. And so I can just rewrite this as 1 over cos squared theta. Now, I know that 1 over cos is equal to secant, and so 1 over cos squared is going to be equal to secant squared. And what do you know, just like that, I've proven my identity. So what I can say now is left side is equal to right side. My next proof is cosecant theta is equal to secant theta cotan theta. So I'm just going to leave my left side the way it is. It's only a cosecant right now, so there's really not much to work with. I'm going to be mostly dealing with my right-hand side right now. So I'm starting off with secant theta and cotan theta. Now my hint last time was to get rid of those reciprocals, so right away I'm going to change it. So I'm going to change secant to 1 over cos, and I'm going to change my cotan. I'm just going to do in a little aside here. I know that cotan is equal to 1 over tan. Now I know that tan is sine over cos, and so it only makes sense that cotan is cos over sine. Now again, if you're not following this, pause the video and do an aside. So I'll just write it in green and then I'll erase it. So I have tan is equal to sine over cos. I have cotan is equal to 1 over tan. And so what that means is that cotan would be the flip of my tan. So it would become cos over sine. Now, at this time, I can go ahead and multiply these fractions together. We know that when we multiply fractions, it's just top times top over bottom times bottom. So I have a cos theta over cos theta sine theta. And since now I have just one fraction, I can go ahead and cancel these out, and I'm left with 1 over sine theta. And we know that 1 over sine theta is cosecant theta, which is exactly what I was trying to get in the first place. Our last example is a little bit trickier. We're proving that 1 minus cos squared theta is equal to sine theta, cos theta, tan theta. So I'm going to go ahead and I'm going to start working with my right-hand side. And I'm going to switch out that tan theta. We know that that's a rule. So I'm just going to rewrite it first. So sine theta, cos theta, tan theta. And so on the next line, I'm going to be left with sine theta, cos theta, and then I'm going to switch that tan to sine over cos. Now, at this point in time, I can scratch off a couple of things. So I can scratch off my cos, and all I'm left with is a sine theta times sine theta, or a sine squared theta. Now, I still don't have what I wanted on the left-hand side. So sometimes you're going to deal with the left-hand side and the right-hand side. Now, 1 minus cos squared theta. I wrote this on the second slide, actually, but because of our Pythagorean identity, the one that says sine squared theta plus cos squared theta equals 1, we were able to rearrange that. So we were able to say that sine squared theta is equal to 1 minus cos squared theta. So I'm able to rewrite this left-hand side as sine squared theta, and I can get, therefore, left side is equal to right side. Now, one other thing I wanted to mention is at this line, if you went and said, okay, I need to turn that sine squared theta into 1 minus cos squared theta, you could do that as well from the exact same identity. So it doesn't matter which way you do this, if you just keep working on the right-hand side, or if you change the left and the right to match. Either way, you're proving that they're equal and you get the exact same answer.